A lot of people say, well, Brian, what's better? Is MyDP better than MHL? Well, I have my opinions, and I'll tell you, my opinion is from a board of directors of VESA. I always think DisplayPort's better than anything else. So I think DisplayPort's better than HDMI. I think MyDP is better than MHL. But it is not my role as an Agilent solution provider to be picking what technology is better. The best technology, it's like wine. You drink wine? What's a good wine? The good wine is the one you like. It's not the one somebody else likes, it's the one you like. It's the one that works for you. So it's the same thing here. All right, we get to have a little fun here. So that new connectivity that I was talking about before, where everybody's got their little smartphones, these things are incredibly high resolution these days. And so, but the thing is you can't put more than two people around a phone, a mobile phone. If you want to share, you need to share over a bigger screen, and so the model now is to connect up. Now, that's a wired model, and that's where we are today. But in the future, it's going to be the case that you're going to sit here with your little device, and you're going to have your thumb. That was a thumb I picked off the internet. And you'll be able to share your pictures with people, much like we used to use slide projectors. You guys probably don't know what slide projectors are anymore because you all look so young. But when I was about your age, a slide projector is what you used to show people where you traveled and the nice pictures you took. Because we didn't all have phones that had cameras, it was a special deal if someone took pictures, and so you had a special device called a slide projector. Well, now you get to sit into the comfort of your chair, you have your friends around, and now you can kind of show pictures. And if it's wireless, someone else who has the same device can be showing their pictures as well. It could be, there could be new games, for gosh sake. All right, now, I know many of you will probably have an entertainment system like this. I just came back from Taiwan. I was visiting Wistron. They design PCs. And they have a room like this. And actually, they had so many meeting rooms filled that I had to have a meeting with them in their entertainment system room, which was a great place because they had a nice TV like this, and they had 7 speakers, and they had little pieces of tape where they were investigating where the optimal place was for the speaker to be, and they had a subwoofer and all that kind of thing. Well, I don't need 32 channels of audio, 5 subwoofers, and delayed systems and everything, and something to rock my chair when I'm watching a movie. I don't need that. And so I have something that looks a lot like this. It's an iPad on a coffee table. And, I'll get my glass of wine, and my wife and I will sit and we'll watch Netflix streaming and watch a British detective movie or something like this. So I am not this, even though I'm responsible for HDMI solutions, DisplayPort solutions, DVI solutions, MHL solutions, EDP solutions, and now MyDP solutions. I do not do that. This whole thing, I don't do that. I do this. A little tiny iPad, that's what we do. Okay, just a little fun there. All right, so let's take a look at this problem. And the problem is you've got your device, and you're going to go ahead and put it onto a big display. And a big display is used not only for its resolution, but because you want to share, right? Because if it was just you looking at stuff, I mean, you could just take your mobile phone and just put it up real close, and that'll be fine. But if you're going to go ahead and talk to a bunch of people, then you'd want to have a bigger display. So you guys are probably familiar with high-definition TV, 1080i and 720p, but we're not getting 4K over 2K out of this link, and I'll show you why in a minute. Although, probably by this time next year, there will be a solution that does 4K by 2K, but let's hold off on that. So let's take a look at your standard high definition. It's 1080i, 720p. And right now, if you take a look at the pixel rate, it's 75 megabits per second, or megapixels per second, and you multiply that by 10 because there's an 8B, 10B encoding. And so the lane bit rate is 750 megabits per second. Now, I'm talking HDMI here, and so when we're talking HDMI, there's 3 lanes. There's red, green, and blue, and so you have to multiply this by 3, and you get 2.225 gigabits per second. So that's the composite bit rate. So if you're going to try to send this over one lane, which is what we're going to do, you need to be able to support 2.23 gigabits per second on your link. If you move to Blu-ray, now you have to have an 8-bit 1080p 60 hertz, and the bit rate, composite bit rate doubles. So we go from 2.23 to 4.46. And of course then if you go to 10-bit, then it increases by another 25%. So here's the point. For DisplayPort, you have a maximum lane rate right now for the technology that we have today. It's 5.4 gigabits per second, where in HDMI, which is the other technology that exists for these displays, the maximum lane rate is 3.4 gigabits per second. So if you just use the maximum lane rate by itself, you could see that DisplayPort can handle both of these while HDMI can only handle the one. That's the fact right now. Now, I will point out that HDMI is moving to HDMI 2.0. Probably the spec will come out in the August time frame, and HDMI 2.0 will have up to 6 gigabits per second per lane. So that would obviously solve this problem. But there's other issues with respect to HDMI 2.0. And I'm not going to be talking about HDMI 2.0 too much more. But if you wanted to talk to me afterwards, I'd be glad to talk about it. All right, so let's take a little bit closer look. One of the things we find that's on almost every tablet or every mobile phone anyway is a connector that looks like this. That's a micro USB connector. And one of the things I found out recently is that a lot of governments have mandated that the micro USB connector be used on all mobile phones and tablets. Now, I didn't know that, but the reason is really about waste. If you have billions of products being made, and if every one of these products comes out with a charger, and the interface is different, then when somebody gets rid of their mobile phone and buys another one a year and a half or 2 years later, then they're going to get another charger. And so now you have all these transformers and iron core systems that are going to be in landfills or thrown in the ocean or something like that. And people are kind of going, no, we don't want to do that. So if you go to a common interface here for charging, now you can change your phone, but you don't necessarily have to change your charger. Seems like a small thing, but it's moving the industry. Here's what's interesting. So you have this micro USB. It's 5 pins. You will not find the word or the letters micro USB. You will not find that in an MHL specification, and you will not find it in a MyDP specification. They'll only say that the MyDP interface or the MHL interface is to exist on a 5-pin connector. That's all they say. They don't say use a micro USB. And the reason is because the USB-IF, USB, everybody knows USB with memory sticks, USB-IF has the trademark on this. So there could be legal issues if you used the words micro USB. So they get around this by just saying, well, we have a 5-pin interface, but everybody knows it's micro USB. Okay, so we have D minus and D plus here on this interface, pins 2 and 3. You got your power coming in on 1, and then there's some sort of ID coming in on 4, and it's usually with some sort of a resistor, and we'll talk about what that requires, particularly for MyDP. But the conclusion is, if you got this interface and you want to throw data through it, you have to throw, you only have that lane, so you have to deal with the composite data. So if I go backward, that means that if I want to do 1080p 8-bit, I got to send 4.46 through this interface, pins 2 and 3. Okay, so it's the composite bit rate we need to think about. All right, so now let's take a look at HDMI interface right now. It's 19. This didn't come out very well. Huh. Okay. Okay, there's a little mistake in the slide, but that's okay. This table here is supposed to be right here, but that's the way it is. Okay, so the idea is you have all these pins on this 19-pin interface. You have 3 pins per differential lanes. So in HDMI you have 4 differential lanes, red, green, blue, and a clock. So that's 12 pins right there. So we're going to compress that all down from 4 lanes down to 1 because that's all we have on this connector. And then there's other low-speed things, which is hot plug detect and CEC bus. And then there's the serial clock and data, which is an I2C implementation. That is all going to be compressed down to one thing. So you have one data lane, one low-speed lane, you have power, you have ground. That's the 5 pins right there. Okay, same sort of thing for DisplayPort. We see right here. So DisplayPort's the same sort of thing. We have 4 differential lanes, got a couple right there, there, and there. So there's 12 pins associated with differential lanes. And then we have a very robust, and I'll talk about this a little bit, a channel called the AUX channel, AUX channel. And it's a differential lane as well. There's a hot plug detect, and I'll talk about this a little bit, but a hot plug detect is a way that a source can know that a sink has been connected. So there's a voltage that comes back. And then there's some configuration pins that are particularly useful for add-on DisplayPort, for instance, DP++. And I don't know if you've heard of DP++, but it's called dual mode, and it allows for a DisplayPort interface to look like HDMI. So that's one thing that DisplayPort's been very good at, is handling the legacy or the previous specifications well. So anyway, we have the data lane. Again, that's 2 lines. That's a differential line. We have 1 low-speed line for all of this, and then we have ground and power, and so that's what's going to be going on to both of these interfaces. Okay, so at this point, we know what the interface is. It's a micro USB connector, but now we're going to talk about MHL. Okay, MHL is Mobile High Definition Link. You could say it's a mobile HDMI link. That's pretty much how it's structured. But it's been owned by this consortium here, Silicon Image, Sony, Samsung, Nokia, and Toshiba. That's 5 companies who own this. Now, when you have a few number of companies that work on a consortium like this, you can move really fast. And of course they have. They've gone from 1.0 2 years ago to 2.0 to 2.1, and they're going to go to 3.0. I think this is actually going to phase out to probably November or December. But they have been moving one revision after another, and it drives me crazy because I'm responsible for a lot of the software development for the applications. So, but they're moving fast because they only have 5 companies that really are involved. And actually, there's only one company who's a silicon vendor, and that's Silicon Image. And so, and they have Simple Labs, which I'll mention is the compliance test house. So they're the ones who are really driving it. So when you only have one company moving, you can go pretty fast. Well, the neat thing about MHL is you have 220 million products now. It has been implemented, and it is off and going. So Samsung phones use MHL, and HTC tablets do. And if you take a look at the number of people doing it, it's like 200 different companies. It's really quite saturated. And there's a number of companies with stereo equipment as well as in automobiles as well. So MHL has been pretty popular, and it's all basically predicated, or what we say, based on HDMI's success. Okay, so we don't see a whole lot of testing coming out of Africa. It's all Asia here. So we got Sony Shinagawa, we got a couple of sites here in Korea, we got Shanghai, Beijing, and Shenzhen. Those are the Simplay labs. And then Taipei with Sony as well. And then Simplay labs in Sunnyvale. So a lot of action in Asia. And I don't get to travel to Europe very often. Not a whole lot of displays happening in Europe. All right, so let's talk about how MHL works a little bit. So I mentioned it's a 5-pin interface. We've got that pretty much nailed down. That's not too hard to understand. So now let's take a look at the HDMI technology. I'm sorry if this is a review, but I don't want anybody getting lost here. Okay, so it's based on Silicon Image's transition minimized differential signaling, what we call TMDS. And this has been out since 1999. DVI, the Digital Visual Interface, was introduced with TMDS, which all had the red, green, blue, and the clock as well. And this TMDS does an 8B, 10B encoding, but it's not your standard 8B, 10B encoding like you find in other technologies, which is the ANSI-based 8B, 10B for PCI Express and DisplayPort and SATA and USB and all that stuff. It is to minimize the transitions. That's what they say here. Transition minimize. The regular 8B, 10B maximizes transitions so your clock recovery can work. Well, Silicon Image says, no, I don't want to have a whole lot of transitions because we're not worried about the clock because we're going to send a clock with it. So they minimize the number of transitions here on the red, green, and blue, and then they send the clock. Now, why would they do this? Well, they would do this because they're interested in limiting the radiation from the HDMI connector. Systems are sensitive to EMI. We have what we call Part 15 specifications, and we don't want these things to radiate. You know, I fly all the time, and the flight attendants say, please turn off your devices, you know, that kind of thing. Well, they're worried about radiation interrupting the measurement equipment in the cockpit. Well, this is the same sort of thing. So what they did is they said, well, let's minimize the number of transitions because the transitions, if you don't have a good match on the differential line, your transitions are going to cause you a lot of radiated power. So that's why they went with this kind of a construction where they have the minimized transitions and they send the clock as well. The clock is always 1/10 the data rate today. So if you have 3.4 gigabits per second on a line, which you don't see too many things do, but for instance, the PlayStation 3 from Sony, that'll have 2.25 gigabits per second, and so its clock will be 220 megahertz, right? But if you had 3.4 gigabits per second, then your clock would be 340 megabits. And that's just how it works. Now, HDMI 2.0, that's going to change. As they get higher and higher, they're going to have, instead of a divide by 10, they'll have a divide by 40. All right? But I won't get into that just now. So anyway, so the way this works is you get the red, green, blue, and you have a channel here like your cable. And your clock comes out here. Your clock continues to come out, but it also gets delayed by this times 10 phase lock loop, which goes and clocks the data. So the data is here, but your clock's over here. But the clock continues on, hits this thing, goes back up to times 10, and by the time it gets here, it meets up with the data again. That's the notion of HDMI. So they're not really too worried about jitter on their clock, because jitter on their clock will convert to jitter on the data, and when that data comes in and gets merged up with the clock again, it'll all cancel out. All right, so that's HDMI. And so we needed to understand that in order to get to the next slide. Okay, so it's like, okay, but you don't have 4 lanes, you only have 1 lane for MHL. So we have to figure out a way to get the 3 data lanes and 1 clock lane onto only 1 lane on the micro USB connector. Okay? So like I was pointing out, then you have 750 megabits per second for high definition TV. Let's take a look at how this works. So you have your red, green, and blue, and you have your clock at 75 megahertz. Notice divide by 10. And what we're going to do is time division multiplex this. And so we'll take the red data, and then we'll take green data and blue data, and then that'll be a full pixel. So we got red, green, blue coming through at actually it's 2.2 gigabits per second, but 2.25 here. So the question is, what about the clock? Because we have 1 differential lane. We're going to take that data we've already got differential on the red, green, and blue. Where do we stick it? Where do we stick the clock on this? Because you just can't add the clock in. Or can you? Well, this is exactly what they did, is they added the clock in. Now, when you do this, they say, okay, we're going to have differential data here, and then we're going to add, basically straight add the 75 megahertz clock. And so this is what your data is going to look like. It's going to jump around like this. Actually, I'll just move over here. You're going to jump around like this, and then you're going to have a clock rise, and then the data moves around up here and then down. So this is the clock, and then this is the data. Now, I said that the clock is 75 megahertz, and the data rate now is 2.25 gigabits. So now there's the point is there's 30 bits, not 10 anymore. It's not a divide by 10; it's a divide by 30 clock. But here's the killer. You have a common mode signal now. Remember, I was saying that the problem with radiation is common mode, and so if you minimize the number of transitions in a skewed system, you'd minimize your radiated power. Well, now all of a sudden they're purposely putting in a common mode signal, so that's going to be a radiator. That's going to be a problem. How people solve it, I think, is dependent on their own IP, but most of the time they'll have to shield it. Okay, the receiver then has to have not only differential but common mode detection circuits. That seems obvious, because what they're going to do is take this MHL signal that's moving 3 times as fast, take the clock out, take the data out, and then repack it back into HDMI. That's what's going to go on. So this is the topology, and I found this on the internet, so I didn't create it. So here's just kind of walking you through. You got the data coming in, red, green, and blue. Pixels at 75, you double that, or you triple that so that you send your data out. You do all your protocol type things. You send the clock out. Now you go ahead and you do the common mode modulation, and now you have a 2.25 gigabits per second stream, and you have channel 0, 1, and 2, which is red, green, and blue, and you're sending out red, green, blue for every clock cycle. Okay? Neat thing about this is that you get 24 bits of color transfer, really nice high definition stuff. Do we need anything more than standard high definition on these little tiny devices? I don't know. My eyes probably aren't that good, but they're 50-year-old eyes. Your eyes are probably better. But everybody seems to want the next resolution. And the reason why it's important is because you're driving these great big displays with it, not so much looking at the small display. Okay, so, but what about 1080p with 60 hertz? That's Blu-ray, which everybody is interested in. So here again, we have, now we deal with a composite bit rate, which is 4.5 gigabits per second. Right now, HDMI was sitting at 3.4 gigabits per second, so there's a conflict here because Silicon Image didn't have the underlying technology to go beyond 3.4 when MHL was created 2-3 years ago. So what they did is they created something called the packed pixel mode. So in this case, what they're going to do is they're going to send the number of pixels that are required for 1080p 60 hertz, but each pixel is going to have 16 bits, not 24. Okay? There's 16 versus 24. So there'll be 5 red, 5 blue, and 6 green. I guess green, our eyes see green better, so a little bit better resolution on green is probably a good thing. So anyway, we go ahead and we increase the pixel rate by a factor of 33%. We diminish the number of pixels by 33%, or multiplicative factor of 0.67, and we end up with twice the number of pixels, which was our objective in the first place, 750 to 1.5. So when we do this, we can do 1080p. So MHL can do 1080p, 60 hertz. The only provision is that it's not 24 bits per pixel, it's 16. And this is the topology for that. So here we have an underlying clock of 150 megahertz. We double that up. Instead of red, green, blue, we play some games on 2 different channels where you share colors. And then again, we go with a 75 megahertz clock. We only do a divide by 2. We do the common mode resolution, so you don't suffer any worse radiation because it's the same frequency we had before. So now it's a divide by 40, not a divide by 30 clock. And we're sending out 4 TMDS symbols of 10 bits each. All right. So let's take a look at testing it. So I think very simply, you have transmitters and you have receivers. Now there's also cables in between, but to me cables are a network analyzer or a TDR type measurement, and it's just a matter of having a fixture and some time. So I think measuring the transmitters with an oscilloscope and measuring a receiver with a signal generator or a pattern generator is really the most significant problem that you'll have, other than the protocol testing of the whole system. But once the protocol protocol has been verified, then there is no ongoing development or change to that. So to test an MHL transmitter, there's something called that C-bus. That's the communication channel for MHL. Then there's power charging. And so the question is how much current does that thing draw? Let me go backwards here. Waveform parametrics is kind of what my specialty is. I've worked in signal integrity testing at high end, so that's obviously where our oscilloscope solutions would play. But there's also the validation that's necessary to make sure you got the link layer stuff. And protocol, main link protocol, sending the proper forms of bits. That's one of your most significant interoperability issues, at least in the intergoing, when you haven't got the right rules in place for your protocol. For testing a MHL receiver, it's the same sort of thing. Does it control the C-bus properly? Does it do the power charging of the device that's connected? Protocol, etc. And then there's something we call the receiver sensitivity. And in this particular case, it's a jitter tolerance. We take a signal and we make it kind of bad. And the question becomes, when does the sync or the receiver break? Or when does it not work right? Well, in HDMI as well as MHL, you have to look at the sync, the display, and you're looking for weird things on the display. So it's kind of strange because it's not a measurement. So what you might see on Monday morning might be a whole different thing than you would see on Friday night. And certainly if you went and had lunch and had some beers, you're not going to see stuff, see the problems that you might otherwise see. So that's one of the problems with MHL and HDMI is the sync doesn't really have a good measurement, or the sync sensitivity doesn't have a really good measurement because it's based on eyesight. All right, so we have a full fixture selection from Wilder Technologies. Wilder Technologies is a company out of Washington State. That's where my house is. And they are very good with signal integrity. They have fixtures for HDMI. They have fixtures for DisplayPort, SATA, Thunderbolt. They have fixtures for everything. They're great. I talk to the designer all the time, and there's a set of 8 fixtures here, and you'd say, well, why do we have 8 fixtures? Well, not only are we going to be testing a mobile phone, which has a receptacle connector, but there'll be dongles that fit into it, and so those need to be tested too with receptacle fixtures as well as plug fixtures. And then there's a number of fixtures required for functional verification, not parametric waveform, but just functional. So these are the fixtures that are used. All right, so in testing a source, so we have our device right here that we're going to be transmitting. We have a fixture with a plug, and that plug has a C-bus coming out, goes to either a silicon image C-bus controller, or it goes to a display with a particular dongle that Silicon Image has used, so that the communication for this thing, the device needs to think that it's connected properly. So you have to have something connected here, and so if you have the C-bus connected, then it will say, okay, I'm connected to something, so now I'll transmit, and it transmits out these 2 connectors here. And then there's another fixture that we have, and I'll talk about the design of this in a minute, but this particular thing has a little probe point here for picking off the clock. Remember, we have the common mode pick-off point, the common mode clock, so that's where you'd pick that off. And then the differential lane comes out and goes to the scope. Now, in the case of testing with a dongle, it might very well be that there's a micro USB to micro USB, just a cable, or it could be that there's some other dongle thing, say a micro USB here and an HDMI here. So in which case there would be an HDMI plug that would fix into here, and then we would go into test equipment as well. So that's why you have a lot of different fixtures. There's a lot of different combinations to be considering. All right, so here's the MHL calibration and test. So we have a big piece of equipment here and something I call signal conditioning. This is splitters and blocking capacitors and cables and this kind of thing. It's not very interesting to have a great big old diagram with all that stuff on there, so I just put one block called signal conditioning, and then we go into a receptacle fixture, those SMAs here into a receptacle, and we use the other fixtures for calibration. So we'll actually go into this fixture here, calibrate with the oscilloscope that signal that I was saying that we really want to make bad. Okay, so we want to make it a whole lot of jitter, and we want to create a problem with the amplitude and really narrow down the eye horizontally as well as vertically. And then we go into the device either through a dongle or through a cable or just directly in, and now we get to send the pattern from our signal generator here, our TMDS generator, and take a look and see if there's any weird artifacts in the display. All right, so that's what's going on with that. And if you just go straight in, it's if you go straight in with an HDMI plug, for instance, that's one of the nice things about MHL is it's supposed to be for devices that are already out there that do HDMI. Now, it turns out there are some issues with that. Some devices, even though they have HDMI, will not work with MHL unless you have a special dongle. So that's what this would be testing with. But some of them can work if you have a special HDMI port. Some of these devices will have, say, 4 HDMI ports, but one of them might be special for MHL. So if you go straight into that one, then it'll work just fine. Because for that particular one, they have the decode pulling all the red, green, blue out and sorting it back into an HDMI signal. Okay, so I wanted to talk a little bit about this, just a little bit more detail here. You can see it kind of plugs in to the phone. There's the C-bus. If you connect it up to a display, then the display talks through the C-bus and everything's fine. Or you can use a piece of equipment from Silicon Image to take care of this and actually measure the C-bus parameters as well. I think it's kind of expensive piece of equipment, but if you're interested in measuring that C-bus, I think that's about the only solution you have. Then we have the bigger, or the other fixture here, which connects up in line. And here you can see a little bit more detail. There's two pins here that we would plug our probe head down into, and then we connect up to here with our SMA connection. And this is what it looks like. It looks like TPA1 takes care of the signaling and passes the signal on to TPA2. TPA2 has the breakout for common mode clock, as well as the differential loading here, 50 ohms on each channel, and is able to, like I said, measure the differential signal. Now, it's worthwhile to talk a little bit about the design, not only of the fixture, but the requirements of it, because in normal high-speed digital systems, it's a 50 ohm single-ended, 100 ohm differential, and they never really talk about a common mode impedance. But in MHL they do. So the fixture is designed with a common mode impedance requirement as well as a differential mode impedance requirement. And it's not a bad idea to go through that real quick, so I'm going to do that here. Okay, so if you have your differential line, which I have here, so that's SMA, you'll notice that there's a 10 ohm resistor that's in series to our probe head here, or to the sink, which is supposed to be 50 ohms. So there's 60 ohms right here, 10 here and 50 ohms to ground. And so if you have a common mode signal, then this is going up at the same time this is going up, this signal here. Okay, so these are, both lines are being basically driven by that common mode signal together. If they're being driven together, then there's no current flowing through these 300 ohm resistors. So these things, since there's no current, it looks like an open. So now you have 60 ohms basically in parallel with 60 ohms because the common mode is driving both of those together. So that's a 30 ohm common mode impedance. And you might say, well, why is it a 30 ohm impedance? Well, for whatever reason, the way the Silicon Image designed the output structure, it looks like the common mode gain of their output is a 30 ohm output, and you don't want a whole lot of reflections, so it's nice to have that common mode terminated properly. Just like in a differential signal, you want that terminated properly so you don't get a lot of reflections. It's the same thing with the common mode. We just don't deal with it very often, though. Now, let's take a look at what happens differentially. If differentially, we got 60 ohms sitting here, but if this signal's going down, then this signal's going up, so there's current flowing here. So but if this is going down the same amount as this is going up, this is basically a virtual ground. So then you have 60 ohms in parallel with 300 ohms, which is 50 ohms. So we have 50 ohms here, we have 50 ohms up top. That's a differential impedance of 100 ohms. Okay? So that's why the fixture is designed with a 10 ohm resistor in there. And if you take a look at the software, we end up with this 1.2 multiplicative factor on our measurements, because when we measure here, we got 50 divided by 60 as a loss, right? So we have to improve that 20%. Okay, so let's just take a look at an MHL signal. I showed you one a little bit earlier but they look pretty ugly, I think. Not good. So here you can see we got a low of the clock, and then there's a high of the clock here, and we've focused in on this section here, and we can take a look at the the signal and the signal complement. Now, one of the issues you have is that the signal and the signal complement needs to have a skew be as low as possible, and you can see here that there's skew here. The blue is actually looks like it's a little delayed over the yellow, and that's going to be a problem. I mean, even though we're doing a common mode clock, you're going to have skew causing radiation at a higher frequency at 2.2 gigabits per second, which may be hard to shield. So it makes for measurement problems, and if you try to manipulate your oscilloscope to make a measurement, you got to realize that half the time it's up high and half the time it's down low, so it's kind of hard. You can't average it. Measuring skew is a tough problem on MHL. So one thing you can do is you can say, well, if you take a look at this, can't you do something with that common mode signal? Like, can't you subtract that common mode clock? Well, you can subtract a common mode clock, but you got to realize skew generates common mode signals. So if you do a common mode detection on MHL and then subtract it, you're going to subtract out the skew as well, and you're not going to see any problem. So we devised a way to do this for MHL 2.0, and basically what it boils down to is if you add the yellow and the green in this case, you would get a signal that looks a lot like this yellow here. Well, you see these points? These are synchronous with the data, and that's this radiation we're talking about, or this common mode. Well, if that is the common mode clock, so if you subtract that out, you're losing all the information directly. So what we did is we figured out a way to keep the common mode edge and filter out the waveform a bit and not get rid of all that common mode stuff, which has to do with the transitions. This is a function of the skew. How much you get. And I had a couple other slides that show you that gets bigger and bigger and bigger the more skew you have. But what was neat about this is that after we implemented it, we went from a variability of, say, 7 picoseconds, an RMS variability of 7 picoseconds, to an RMS variability of like 500 femtoseconds or something on a measurement. So we're always looking for new ways to do things that solve these kinds of problems. So here again is if you remove the common mode clock, you'd see a nice waveform, but that removes the problem because the common mode is the radiation from the edges. So what you want to do is you want to smooth the clock and not get rid of those particular edges. And so you can see here it looks a lot more hashed than over here because we've kept the clock integrity, but we haven't. We have filtered out the transitions that were occurring between the clock edges. All right. MHL tests under different conditions. It's a 3.3 volt standard, much like HDMI, except for they want you to do all the tests at 3.4, and they want you to do all the tests at 3.15. And that's just the way Silicon Image wanted to do it. So they doubled the test time right off the bat. Okay, the bit rate is a function of the resolution. So there's 200 well, I got to be careful. There's 750 megabits per second all the way to 2.2 gigabits per second, and now there's even more for MHL 2.0 and 2.1. It goes up to 3 gigabits per second. Okay, so that's what we got covered here. Okay, so just going through, we have an application. We actually have it demoed, so if you want to take a look, you can do that. You can pick your source device. This is an application framework, by the way, that we use for all of our apps. So once you use it for one application, for one interface, you're good for a lot of them. So you can pick your CTS, CTS 2.0, CTS 1.2. Actually, we're going to probably put in CTS 2.0 in here soon as well. I just found that out today. And you can now with CTS 2.1 test only with single-ended. So instead of doing differential and having a common mode pickoff, you can do 2 single-ended connections on that differential bus and not worry about that other common mode pickoff point, which is actually, it helps accuracy quite a bit. So you set that all up, and after so doing, you got 1, 2, 3, you move on to select tests. When you move on to select test, you can see that there's a whole bunch of single-ended measurements you have to do, a whole bunch of differential measurements, differential output, rise time, fall time, there's output voltages, and there's swings and that kind of thing. And then for, there's common mode measurements here. So there's a lot of clock jitter and common mode output swing and rise and fall time. And then there's a lot of data eye measurements we make as well. One of the new additions here you see is the addition of 43, plus 43 and minus 43 picoseconds of skew. That's because they were having so much problems, mainly with our competitor, on making that intra-pair skew measurement, that they changed the methodology so that it would be easier. So now in MHL 2.1, they now include this skew channel. So what it means, it makes it harder for you to understand what's going on, because we take the measurement or take the acquisition and we have to embed a channel that has skew in it and then do the eye diagram. So if you're going to try to get the same results that we get, you have to use the same channel models mathematically. Okay, so this is the new, this is a setup when you get into this and it says to connect up. We tell you how to do it. We give you all the instructions. And in this particular case, since we got 2 single-ended connections here, this is a now 2.1 mode. We don't have to connect up to the common mode clock anymore. We can actually, if you take 2 single-ended lines of a differential bus and you subtract them, you get the differential signal. If you add and divide by 2, you get the common mode. So what we're doing here is we can go do the differential, but we can process the common mode as well at the same time. So what we'll do is we'll take a trace of both, and then mathematically we'll subtract them, we'll come up with the differential, mathematically add them, divide by 2, we come up with the common mode, and now we can go do the eye diagram and that kind of thing. Okay, some other things that you can do. You can add in your own tests into our applications. So this is just your standard thing. This is all applications. It's not just MHL. You can also do some scripting, and you can control this remotely with a scripting language. A lot of people like to do this remotely, like to control the applications. I deal with one guy from Granite River Labs, and he controls one of our scopes in San Jose from Oregon. So right down the coast, about as long as probably as Korea is, and he doesn't have to go down to San Jose. He can make all his measurements remotely. Okay, so now I'm going to talk a little bit about MyDP. I'm going to shift gears into one of my favorite topics. It's MyDP. That's the Video Electronic Standards Association. We have 200 member companies. So we can't move as fast as Silicon Image can move on MHL, but we move pretty fast. In 18 months, we've come up with 18 different standards that we've modified. So we have a lot of work groups doing a lot of things in parallel. So we do get some speed, but it's speed with a lot of industry input, and I think that makes us more applicable, gives us better product in the long run. So the compliance testing hasn't started, but I think it's going to start 2013, June, excuse me, and it goes 5.4 gigabits per second. This is 280, 60 hertz, as I showed you before. DisplayPort at 5.4 can support 1080p 60 hertz directly today, and MyDP does. So the CTS just came out last month. we got a device out there. We're trying to make things work. Some things have been implemented. LG's got a phone out there with MyDP, and there's a lot of tablet manufacturers looking at it right now. It looks like it's going to be a popular standard. One of the neat things about it is you go with your micro USB, you can change to a VGA, micro USB to HDMI. We do that already. HDMI didn't go to DisplayPort, HDMI didn't go to VGA, but with DisplayPort we kind of feel like as the second standard coming in, we have to address the legacy situation because people have an installed base of equipment. So there's a lot of these dongles. Lots of dongles out there. So, but it's all addressing people's installed material like overhead projectors, etc. Okay, you could say it's not very new because it's just DisplayPort. Although some of the early implementations seem it's a little different than I would expect. So, long term it'll be the same as DisplayPort, but that's the theory anyway. Okay, so what I'm going to do is go through some slides, but they'll be paired together. So I'll show you one which is DisplayPort, and then I'll show you the MyDP version. And the reason I want to show you that is once you understand DisplayPort, whether it's DisplayPort box-to-box or DisplayPort EDP, which is an embedded DisplayPort, or MyDP, all the coding, all the overhead is the same. So once a company decides to go do EDP, for instance, MyDP is a snap. And EDP is actually a very, very strong technology for driving panels and saving battery power. So, so there's this economy of engineering knowledge, I would say, when it comes to DisplayPort. So these will be paired together just for your information. So DisplayPort looks like this. You got 4 lanes. You got an aux channel. Fast aux is for USB transport, but nobody's implemented this. And you have a hot plug detect. And I'll talk about how this works in a minute, but that's the interface. If a receiver needs help, it can hit the hot plug detect, interrupt, and then over the aux channel there can be communication back and forth to optimize the link. Okay, so this is what DisplayPort does. And when we get to MyDP, it's the same thing, except there's only one line here, not 2 lines. So suddenly your differential signal is turned to single-ended, so your sensitivity is reduced by half, and you do have a radiator basically at the aux lane rate, which is 1 meg, which is not much of a radiator. And it's single-ended, and in order to handle the hot plug stuff, since it's gone from the interface, you have to poll. Every now and again the source has to come and ask the receiver what's up, and the receiver has to come back and say everything's okay or everything's not okay, here's what I need. Okay, the silicon structures, it's inherited from PCI Express. That's one of the good things about DisplayPort. It's in a lot of silicon already. It's there for the PLL bandwidth is 10 megahertz on the highest data rates. And there's a jitter tolerance curve specified. That jitter tolerance has to do with jitter versus frequency. That's where I was talking about how to test it. You put in a lot of bad jitter, and they have a curve. And if you go above that, then they say that, or you must reach the minimum of that. You go above it, you're okay. That's good margin. So the data rate, if you support 5.4, then you have to support 2.7, 1.62. So here's what happens when you go to MyDP. Not much. MyDP supports 5.4. It has to. That's the way it does because that gives you 1080p, 60 hertz. All right. Each lane is differential 100 ohms. We already talked about that. You have 1, 2, and 4. Standard 8B, 10B. Each lane has separate clock recovery. The other thing I'll point out is in test, that clock recovery or that receiver testing is measured with an onboard bit error detector. So it's not with your eyes, it's actual measured. So that's another thing about DisplayPort that's important to note. And the way this thing is configured is so we have 50 ohms outputs, 50 ohms impedance, and we have a capacitor connection between the two. And for MyDP, it's the same thing, no big deal. Okay, That's why I say it's the engineering economy is there. Okay? You don't get different voltage swings, different preemphasis, or different bit rates with MHL or HDMI, but you do with DisplayPort. 4, 600, 800, 1200, and then all these different preemphasis settings as well. The issue is monotonicity, which means if the receiver wants more power, it gets more power. Okay? Not a specific amount of power, it just gets more. So if it asks for 800 millivolts and it only gets 650, but it started at 400, that's okay. So we have fairly loose specs, but we want to make sure that if it wants more preemphasis, it gets more, not necessarily a prescribed amount more. That's the thing. We also have spread spectrum clocking, which is incredibly important when it comes to this radiated emissions thing. If you spread your signal, it doesn't come up as high. That's one of the problems MHL and HDMI have. It has fixed radiators, and it goes high. All right. I wanted to show this just quickly so you can understand the link of a DisplayPort device. So, let me move back. So it starts off, the source goes ahead, and when the receiver is plugged in, this voltage comes over here and it says, I'm in there. And so the source can go, okay, what are you? And it can go ahead and read the EDID, the electronic display identifier, and read what we call the DisplayPort configuration data. Reads this information and says, oh, I know what to do with you. Sets up a particular bit rate. And then there's a lock process. And if there's a problem with the lock process, it sends back over here to the DisplayPort configuration data and issues an interrupt. And so any time in the link, existence of the link, there's a problem, the receiver can always issue a hot plug and say, I need more assistance, I need more power. All right, so that's the big thing. So when we moved up MyDP, a lot of that stuff goes away. You don't have the hot plug interrupt anymore. The source has to periodically ask, is everything okay, Mr. Receiver? That's the only difference in addition to the voltage there. Okay, this is some signaling with the aux channel. I won't get into the details so much about that, but notice there's a lot of pull-up resistors. This is for source and sync detect assistance so that you can turn off syncs if there's not a lot of action or anything. You can know that you're plugged in. And when we go to MyDP, it gets greatly less because there's only one line. Okay? Pretty simple. All right? The MyDP requirements here, you're just going to go ahead and have a dongle that connects up. So this is a MyDP source. This is, of course, happening over the micro USB. It needs to know that it's MyDP, not micro USB or USB. So the way that happens is with this 620K ohm resistor on this line. It sees this 620K and says, okay, I am DisplayPort. I'm going to do MyDP. And then it sends out the data. And we show that outside here in the demo. The rest of this thing here, this is a DisplayPort sync, so there's no such thing as a MyDP sync. It's a DisplayPort sync, and so when it looks this way, it looks like it's seeing DisplayPort source. That's what this is all about, 100K here and all that. But when this, when this is looking downstream, it has to see the 620K to think it's talking MyDP. Won't go into this, but what this is a flow diagram for the aux channel communication to do the frame sync up when it's sending the data to the sync. And so it needs to go through a flow diagram, and anybody who's designing in DisplayPort needs to understand the link training requirements. And so I put two of these here. There's different patterns that are being sent and depending on where you are here, whether you're talking preemphasis or setting for level or achieving lock. Okay, so I think of it the same way. There's MyDP transmitters and MyDP receivers. No, there's DisplayPort receivers. So a lot of this goes away in terms of our solution. It's the same. And when it comes to DisplayPort or MyDP test. It's really a DisplayPort solution. That's what we would show you at our demo. The fixtures are very small, and unfortunately, when I created this slide set, I only had artist renderings of these, but I actually have these fixtures at the demo. I have 2 sets of MyDP fixtures, the only 2 sets in the world that exist right now, because just before I left for Taiwan, Wilder Technologies gave me right off the production line all the fixtures that are needed for MyDP. Okay, very simple schematic here. This is a functional test. In order to verify that 620K resistor, you connect up a high resistance and a low resistance, and it better not work, and then you put it up to 620, and if it does, then that's just a functional test that it's working properly. Okay, similar type construct we had before. We have our mobile phone. We connect up to it with a fixture. If we do automation, we connect up with another fixture going to an aux channel controller, going to the oscilloscope, and we run our application on the oscilloscope. And in this particular case, we have a MyDP personality, which isn't much different than our regular DisplayPort. So it's pretty simple. The automation here has is something that we'll get going. It's not working right now on the current phones that are out there, but the next revision or the next generation of phones will see that happen. So this just speaks of the automation, being able to set up your data rate, your lanes, and all that kind of stuff without doing any test. You want to verify you have control, so this is what that software allows you to do. The other thing I'll point out is in sync testing, there's no such thing as a MyDP sync, but there are such things as dongles that convert to all these different standards. We wouldn't test the output of these, although if you're a developer, you would. But you have to be able to send a DisplayPort signal to here, to the front end of the dongle, and it acts just like a regular display thing device, and would you'd be counting errors and that kind of thing with a bit error ratio tester. Okay, summary of technologies. Then I guess I'm getting finished. MHL enjoys great market presence. Got 200 million products out there. It'll probably double by the end of this year. And MyDP is just coming out now, so it's a latecomer, but it looks like it's got a nice capability in terms of radiated emissions, in terms of the economy of engineering, and in terms of data rate, it certainly seems better. So there are TMDS is raster based. That means it depends on the timing of the display, while DisplayPort is packet based. It doesn't really care. It'll just send out the data in a packet, and there's a video field in there, but it's not connected to the raster of the device. MHL has a common mode clock, which can radiate, can be a problem. MyDP clock is derived from transmitted data. That is with that standard 8B, 10B encoded that gets where it's pulled out. MHL can do 1080p 60, but with only 16 bits versus 24. The sync testing is visual on MHL, but on MyDP, it's an onboard bit error ratio measurement. Same connector, micro USB. Same use model, you got to go ahead and send it to a display or a television, but really nothing else is in common with these technologies. Okay? Thank you very much. I'll be out for be able to handle any questions that you might have. Thanks a lot. Okay. Yeah.